All right, welcome. You hear about large language models, or LLMs, absolutely everywhere these days. They seem to think and create and even reason, and it can feel like actual magic, right? But today, we're going to pull back the curtain and show you that at its core, it's actually something you're probably pretty familiar with: math. So let's get right to it. The big question. When you type a prompt into an AI and it starts spitting back a response, word for word, what is actually going on under the hood? How does a machine that only gets ones and zeros manage to write poetry or debug code or explain quantum physics? That's the mystery we're going to solve together. We're going to peel this whole thing back in 4 layers. First up, how do we get from words to numbers? Then, once we have numbers, how does this digital brain actually learn to think? Third, we'll talk about the single biggest breakthrough that changed the game. And finally, we'll look at how you take all this incredible tech and turn it into something people can actually use. All right, first things first, the absolute foundation. Before an LLM can even think about writing, it has to translate our messy, nuanced world of language into its clean, logical world of mathematics. This first, crucial step is called tokenization. It's basically the process of chopping up a sentence into little pieces. Could be whole words, parts of words, even punctuation, and then assigning each little piece a unique number. We call that number a token. And why do we do this? Simple. Computers don't speak English. They don't understand love or logic. They only get numbers. Tokenization is the universal translator between us and them. And that right there is the key. The entire job of a large language model is to do one thing, and one thing only: predict the next most likely token in a sequence. It looks at a string of number tokens and just calculates the probability of what the very next token should be. It adds that to the chain, and then it does it again and again and again, building out a sentence one number token at a time. Right, so it predicts the next number. Simple enough. But how? How does it know which number to pick? How does it learn that after the tokens for the capital of France is, the next token should probably be the one for Paris? Well, that's where the training comes in. Now, this is going to sound crazy, but the core idea behind all this, you probably learned it in high school. It's just a souped-up version of the formula for a straight line. An LLM is, at its heart, a massive, unbelievably complex mathematical function. And just like with a simple line where you need to find the right values for M and C to make it work, an LLM needs to find the right values for its own parameters. Okay, but here's where things get absolutely wild. A simple line has two parameters. A modern LLM, like GPT, it has over 100 billion of them. And finding the perfect value for every single one of those parameters, well, that requires an insane amount of data to learn from. So where does all that data come from? Basically, the entire internet. We are talking terabytes upon terabytes of text from books, PDFs, Wikipedia, Reddit, Quora, you name it. This whole process is called pre-training. The model just reads and reads, breaking down sentences, looking for patterns, and slowly, over trillions of examples, it tweaks its billions of parameters to get better and better at predicting that next word. But how does it learn from its mistakes? Well, that's where something called a loss function comes in. Every time the model makes a prediction during training, the loss function calculates how wrong it was. You can think of it like an error score. The model's only goal is to get that score as close to zero as possible. It makes a guess, gets a score, adjusts its parameters a tiny bit, and tries again. Trillions of times. Now, after all that pre-training, you get what's called a base model. And let me be honest with you, it's kind of useless. Sure, it can predict the next word, but it has no common sense, it makes stuff up, it can be biased. It's like a baby that can see and hear but has zero morals or understanding of the world. To make it truly helpful, it has to go through post-training, where humans carefully fine-tune it with high-quality examples to teach it how to behave and how to be a useful, aligned assistant. Okay, so we've got this giant math brain that's read the whole internet. But for a long time, these models they weren't that great. They were missing one crucial piece of the puzzle: context. They lose track of what was said earlier in a conversation. And then, bam, in 2017, a single research paper dropped, and it changed everything. See, before 2017, models had to read sequentially, one word at a time, in order. It's like trying to understand a movie by looking through a keyhole. You just can't get the big picture. But this paper from Google titled Attention is All You Need introduced a new architecture called the transformer. It allowed models to look at every single word in a sentence all at once, in parallel. This new superpower is called the attention mechanism, and it's exactly what it sounds like. It lets every single word in a sentence pay attention to every other word to figure out the relationships between them. This is how a model knows that the word bat in "the bat flew out of the cave" is an animal, but the bat in "the player swung the bat" is a piece of wood. It finally understood context.
And the name of the paper says it all. Attention is all you need. This was the key. It was the breakthrough that unlocked the true potential of these models. In fact, the T in GPT stands for transformer, the very architecture from this paper.
But there's a catch. Processing everything at once like this takes a staggering amount of computing power. And it just so happened that the perfect tool for the job already existed. GPUs, the graphics cards originally built for video games. And who was the leader in GPUs? NVIDIA. They were in exactly the right place at exactly the right time, holding the hardware keys to the entire AI kingdom. So we've got the tech. It's groundbreaking, it's powerful, it works, but a powerful tool is just a tool. That brings us to our final and maybe most critical piece of the puzzle. Now that you have this hammer, what do you actually build with it? And this brings us to what might be the most important rule in building anything great, not just AI products. You must always start with the user's problem, not with the cool new technology. If you start with the tech, you end up building something that's technically amazing, but that nobody actually wants or needs. The product legend Marty Kagan gave us this incredible framework, these 4 essential questions you have to answer. First, and most importantly, is it valuable? Does this solve a real problem for someone? Second, is it viable? Can our business actually support this and make it work? Third, is it usable? Is it easy and intuitive for a person to figure out? And only then, fourth, do we ask, is it feasible? Can our engineers actually build this thing? So if you're a product manager working in AI, look at it this way. Your job isn't to be the world's leading expert on the tech. That's feasible. And it's actually the smallest slice of your pie. Your main job, where you spend most of your time, is on making sure the thing you're building is valuable to users, viable for the business, and usable for humans. The technology is just the means to an end. So we've covered a ton of ground, from words becoming numbers, to training a digital brain, to the attention breakthrough, and finally to building real products. You now have a really solid mental model for how all this stuff works. But let me ask you a question. How well do you really get it? I've got a simple little test for you, a self-assessment, if you will. Go to ChatGPT or any other LLM. In your own words, just write out your explanation of how it works. And then ask it to rate your understanding on a scale of 1 to 10 and tell you where the gaps are. It's a fantastic way to check your own knowledge. Because they say the best way to really learn something is to try and teach it, even if you're teaching it to an AI.